Hello everyone. So far, we've been solving differential equations algebraically by separating our variables and then integrating. Before we did that, we used a graphical approach when we used slope fields to sketch an approximate curve through a given point. Remember, when we had the slope fields, we could actually visualize the family of solutions. Now, we're going to try a numerical approach for approximating the solution to a differential equation, and that's called Euler's method. And yes, I know it's spelt with an EU, but it's actually pronounced like Euler's, okay? Like an oil rig. So, Euler's method is a numerical technique for approximating solutions to ordinary differential equations. When an exact algebraic solution is not possible. Now, I'll be honest, we're going to start with ones that we can algebraically solve, just so you can see how the method works. Now, Euler's method is based on the assumption that the tangent line to a curve is a good approximation of the curve over a given interval. And it's really only a good approximation over a small interval, isn't it? Okay. All right. Now, this method is used to approximate the solution numerically. I should have made this line longer. To a differential equation. And we manually create the solution piece by piece using short line segments. And we're using those tangent lines, okay? So we're going to use short line segments. Now let's look at an example we can solve algebraically. That way we can make predictions and we know when we do it, we'll see how accurate it is. So we know that if we have this dy dx equals y, we can separate the variables and have dy over y equals dx. Next, we integrate both sides, and the antiderivative of 1 over y is the natural log of the absolute value of y. Antiderivative of dx is x plus a constant, which I'm going to call c1. Now I'm going to change from log form to the exponential form, so the absolute value of y equals e to the x plus c sub 1. If I drop my absolute value, I have to have a positive and a negative on the other side. And if there was addition in my exponent, that means there was multiplication with the same base. Also, we can look here at this positive and negative 1 times an e raised to the c1 is another constant c sub 2, and we multiply that by our e to the x. So we now have the general solution. But we were given an initial condition, y of 0 equals 1. So let's substitute that in. That means that 1 would have to equal c sub 2 e to the 0. And e to the 0 is 1, so we know that c sub 2 is 1. So when we substitute, we don't have to write 1 times e to the x. We just know that our solution is y equals e to the x. So we looked at the differential equation with the given initial condition. We know the actual solution. Now, we're going to use Euler's method, and we're going to let delta x be 1 for 3 steps, okay? Now what I have here is I have a point sub 0 because that's our initial point. That's the point we know. And 3 steps, I'm going to need a point 1, a point 2, and a point 3 after it, okay? That's where my rows came from. Now remember, our dy dx is still y, and our initial condition was y of 0 is 1, which means the first point is 0, 1. Now our slope is dy dx equals y. So when we have the point 0, 1, our y value is 1. So that's our slope. Okay, so remember, this is our slope. Now our new x value, we're going to take the 0 and we're going to add delta x. So we're going to take the x value that we have and we're going to add delta x. So 0 plus 1 is 1. Now to find the new y value, let's actually plot this. If we start at the point 0, 1 and we use the slope of 1, it means go up 1 and over 1. Okay? Oops. And this line, so this was our point 0, 1, and notice our new point is at 1, 2. So our new y was 2, right? Okay. Now, so notice that line was tangent at the point 0, 1, but it's not tangent now that we're at 1, 2. We're going to use this point 1, 2, our new x and our new y, and we're going to find the slope at this point. Well, dy dx is y, so our y value is 2. So if our slope is 2, from this point 1, 2, we have to rise 1, 2, and run right 1, and we're going to connect that. So this new point is 2, 4. The old x was 1. We add delta x, we got 2. And our new y is 4. Now I'm going to bring this down here because this is our second point that we found. And if this is our point 2, 4, our slope is y, so it's 4. So from this point, we're going to use our slope, rise 1, 2, 3, 4, run right 1, connect, there we go. So now this new point, our x value is 3, right? 2 plus our delta x1 is 3, and our y value is now 8. Okay, so we're going to bring that down here. Our point is 3, 8. That's the point we're at now, which means what is our new slope? Well, it's equal to the y value, so it's 8. Oops, I forgot to write my 8 down here. Okay, now when I use my slope and I go up 8, which I can't do in this picture because my graph paper is too small, but that's okay because I wanted you to think anyway, which is why it's too small. Our new x, right, we would take the x plus our delta x, so 3 plus 1 is 4. Now, how are we going to find the new y value? We're already at a height of 8. Right? And our slope is 8, so we're going to have to rise 8 more. So if we're at a height of 8 and we're going to go up 8, our new height is going to be 16. So our new point is the point 4, 16. Okay, and there we go. And you can see the graph that we're using is made up of all these connected line segments. And you can also see that the further we go from our initial condition, the further away our approximation really is from the actual curve, okay? That it gets worse as we get further away. So for Euler's method, we start with a point which we'll call x naught, y naught. That's our initial point, right? That's the initial value that we're given. Okay, that's our starting point. Now, from there, to get to the next point, whether we're doing this for the first iteration or the 10th iteration, we have to add delta x to our x value, because this length is delta x. And this length is y1 minus y naught, right? The change in the y's, it's also the change in the y's, right? The slope of that line is change in y's over change in x's. So our change in y would be y1 minus y naught over delta x. So if we're finding x values, think about this. X sub 1, we would take the initial x value and add delta x. If we want to find the second one, we would take x1, the x that came before it, and add delta x. If we want to find x sub 3, we take the x value that came before it, x sub 2, and add delta x. So this is a recursive sequence, right? So x sub n would be the x term that comes before it plus delta x. This is how you find the x's. You take the x value that came before and add our change in x. Now, how do we find the y values? Now, remember, the slope, so when we started the initial, that slope we were looking at, so the slope of the initial point is the y1 minus y0 over delta x. I'm going to multiply both sides by delta x, and I'm going to have slope times delta x equals y1 minus y0. Now, if I add the y0 to the other side, I have my initial slope times delta x plus my initial y value, right? Now, we could go through the whole process with the slope and multiplying and bringing it over, but what do you think y sub 2 is? It's going to be the slope of the previous line times delta x plus the previous y value. Y sub 3 is going to be the slope of the previous line times delta x plus the previous y value. So for any value of y that we're looking for, we use the slope for the previous one times delta x plus the y value from the previous one. Now keep in mind here, guys, where is this slope coming from? Slope is the derivative dy dx. So let's go back to the same example we had, where we had dy dx equals y. So it's the same one that we had before, only this time we're going to let delta x be 0.5. So our initial value is, we're still going to use that y of 0 equals 1. So we're still starting at that point 0, 1. And I know I like to write it as a point so I remember. So my slope here, okay, is dy dx evaluated at that point. So it's just the y value 1. My new x is my old x 0 plus my delta x 0.5, so I'm going to get 0.5. Okay, so now we want to find our y value. So our y is our slope 1 times delta x, which is 0.5, plus the previous y value, which was 1. That's going to give us 1.5. So if we look at the graph, from this point 1, 1, we're supposed to end at the point 0.5, 1.5. And see how much closer this tangent line is already? We like that, right? This is the point 0, 1. This is the point 0.5, 1.5. Okay, now we're going to use that 0.5 and the 1.5. And now, what's our slope? So our slope at this point is 1.5. If you're graphing, you might prefer that as 3/2, right? And our new x is going to be our old x 0.5 plus 0.5, which is 1. Now our y value is going to be the slope 3/2 times our delta x. Now 0.5 is the same as 1/2. Whatever is easiest for you to do the computations with, that's fine, even if you're using your calculator at this point. Plus our old y value was 1.5, or 3/2. So 3/2 times a half is 3/4. Plus, but if I want to add 3/2, I need a denominator of 4, which means I have to double the numerator. So we get 9/4, which, if you want, you can use 2.25. It doesn't matter. So now I'm going to plot that point 1, 2.25. And if we draw that tangent line, we can see how much closer it is. It's still not perfect, but it is definitely closer. So our next point, what did we say? It was 1, comma 9/4. And again, like I said, I don't care if you're using fractions or decimals. That's totally up to you. And our slope is the y value, 9/4, or, like we said, 2.25, does not matter. Now our new x, we're going to take the old x1 and we're going to add 0.5, so that's 1.5. Our new y value, we take our slope, which is 9/4, times delta x, which is 1/2, plus the y value was 9/4. So 9/4 times 1/2 is 9/8. Now I want to add 9/4, but I need a denominator of 8, so I need to double the numerator, and that's going to give me 27/8, which is 3 3/8. So that's not going to round nicely, but that's okay. So we're going to go to 1.5, 1, 2, 3, and not quite a half. Then we're going to connect, and there's our tangent line. So we still have another iteration to go. So I'm going to bring down this 1.5 is our x, and 27/8 is our y. Our slope is the y value, 27/8. To find the next new x value, we take 1.5 and add our delta x, so that's 2. And to find our new y, we take our slope, which is 27/8, times our delta x, which is 1/2, plus our y, which is 27/8, equals, and like I said, you can pull out your calculator if you want to. I've got 27/16. I want to add it. I need a denominator of 16, so I double the numerator to 54. And when I add, I'm going to get 81/16, which is 5 1/16. So now at 2, we're going to be 1, 2, 3, 4, 5. Really close. Now, it's still not a perfect approximation, but you can see that it's a better approximation than when we had a delta x of 1. Okay? So it gets closer. And if you look at the actual y values, when x was 1, the y value is 2.7, ours was 1.5, versus over here, it was 2. Same thing when x was 2, the matching y value was 4. On this one, when we're at x equals 2, our y value is 5 1/16, and the actual one is 7.38. So we're definitely closer. It's still not perfect, but it's definitely closer using a smaller delta x. So the answer here, oops, I didn't write it, is definitely delta x equals 0.5. Now, the graph below illustrates the particular solution as it compares to the Euler approximation. So you see we have the solution curve, and then you have each of the tangent lines for the Euler's approximation. Why do the approximate y values underestimate the actual values? If you think, remember this is the curve y equals e to the x, but the graph of y equals e to the x is concave up. Now remember, Euler's method relies on tangent lines, and when we have graphs, tangent lines lie below when a graph is concave up. So since y equals e to the x is concave up, each tangent line lies below the curve, leading to Euler's method being an underestimate. Are the approximations getting worse? They are definitely getting worse, right? Each time our approximation line is getting further from the curve. So they are definitely getting worse. Why is that happening? Well, we have an exponential curve, and exponential curves grow much quicker than linear curves. So this is because y equals e to the x starts to grow very rapidly, right? Exponential functions grow much faster than linear functions. Now my next question for you is, what can be changed to make the Euler solution curve more accurate? Well, it's what we talked about in the previous one. We need to make delta x smaller. More steps equals more accuracy. Now here I have a summary of what we do to actually use Euler's method. You begin at, and this xy was the one that we called x naught, y naught, specified by your initial condition, okay? Use the differential equation to find the slope at that point. You're going to find x by adding delta x. So we take the x and we add delta x. We're going to increase y by a small amount delta y. Remember, that was our slope times delta x, and then notice we're going to add the old y value. So this was our y sub n equals m sub n minus 1 times delta x plus y sub n minus 1, just so you can see it that way. Now using that new point, we go back to step 2 and we repeat the process as many times as we need to, okay? Now, if we are, with our method, always moving to the right, if we need to move to the left, we repeat the process using negative values for delta x. So instead of adding 0.5, we would subtract 0.5, okay? And guys, that's Euler's method. We will definitely be doing more in class, and I'll see you all soon. Bye.